Okay, so think about this challenge, right? Building an AI that really gets what it's seeing, not just
Mm-hmm.
in pictures, but in videos too. You'd want it to like spot objects, understand how they're laid out, maybe even read signs or text.
Mm-hmm.
But traditionally, we've kind of attacked this by building different AIs for each little thing. One for objects, one for actions, maybe another for text.
Exactly. Which, works for those specific tasks, but it gets messy. You end up with this complex patchwork, not really one system that sees the whole picture. Excelling at image recognition often needed a totally different training setup than, say, understanding video.
Right. Reading text in an image, that was
Yeah.
another specialization. So yeah, impressive results in silos, but hard to get that single comprehensive visual understanding.
Precisely.
Okay, let's dive into that because this deep dive, we're focusing on something pretty exciting that might just change the game. It's a new approach called the Perception Encoder, PE. We're digging into the research paper behind it.
And the core idea is, well, it's kind of surprising, actually.
Yeah.
They found that this technique, called global vision language contrastive learning, basically teaching the AI to connect images and videos with text descriptions, that alone can teach a model features that are state-of-the-art for a whole bunch of different visual tasks downstream.
So just by learning this image goes with this text,
Mhm.
it somehow picks up all these other skills.
That's the fascinating part. The model just unexpectedly develops this really broad skill set. The paper shows that inside this one contrastively trained model, you find features that are really well suited for OCR reading text.
Okay.
Visual question answering, object grounding like linking words to parts of an image,
hmm
even object detection, understanding depth, tracking things over time. It's quite a list.
Wow. Okay, so here's where it gets really interesting then. They actually compared this PE encoder against other top models, right? Models specifically trained using things like captioning or spatial self-supervision.
They did, and get this. Certain layers inside PE, even when you just freeze their features, don't train them further for the specific task. They perform just as well as, or sometimes even better than, those specialized models.
Okay, that's pretty significant.
It really highlights the potential here. If you step back, it suggests we might be able to scale up one sort of simpler pre-training method to handle a huge range of vision tasks.
hmm
Could really simplify how we build these systems.
Make them more versatile, more efficient. And they didn't just keep this to themselves, did they? They released stuff.
That's right. They've made their models available, the code, and even a new data set they created called the PE video data set. It's all out there.
Great. So our goal today for this deep dive is to really get under the hood of this perception encoder, understand the core ideas, and how this unified approach pulls off such, well, surprisingly diverse visual skills.
Exactly. We want to cut through the jargon and really grasp the essence of how PE works and why it might be a pretty big leap forward for AI.
So that central idea, contrastive learning as this unifying force, can you elaborate a bit more on that core finding? That just this global vision language, contrastive learning, gives you these state-of-the-art features for so many different things.
Absolutely. So the core mechanism is teaching the model to tell apart related pairs, an image and its correct description from unrelated pairs. That's contrastive learning 101.
Right. Match versus mismatch.
Exactly. And what they found is by doing just that on a large scale, the model implicitly learns this incredibly rich visual understanding. The surprising part isn't just that it gets high-level concepts, which you might kind of expect from vision language training. It's that it also learns features crucial for tasks needing really detailed spatial understanding, or even, like we said, reading text embedded in the image.
And you mentioned these specific features popping up for OCR, VQA, grounding, detection. How did they actually pin that down? How do you know those features are there?
Right, good question. It involves a lot of careful probing and analysis inside the model. They basically took the trained PE model and tested different layers on various downstream tasks.
Okay.
So they could see, okay, layer X seems really good for recognizing text characters, while layer Y activates strongly when you need to answer spatial questions about the image. It's like dissecting the model to see which parts learned which visual concepts or reasoning skills during that initial pre-training.
Got it. And that comparison to the captioning models and the spatial self-supervised ones, the fact that PE's frozen features held their own, even beat them sometimes. What does that really tell us?
It strongly suggests that this global contrastive objective teaches a more general, maybe more robust form of visual understanding, compared to methods that focus solely on, say, generating captions or predicting spatial layouts without that language grounding.
So it's less specialized.
Kind of. It seems like certain layers in PE capture fundamental visual information that's just broadly useful across way more tasks. That vision language alignment seems to encourage features that aren't, overfitted to just one type of problem.
Which opens up that exciting possibility. You mentioned scaling one simpler pre-training method.
Yeah.
What are the big implications there for AI development?
Oh, they could be huge. I mean, think about it. Instead of juggling a whole zoo of specialized models, maybe you could rely on one foundational model, like PE. Adapt it, fine-tune it for different applications.
That would save a ton of resources, right? Computation development time.
Exactly. And it could also make integrating different visual skills into AI systems much more seamless.
And releasing the models, the code, that new PE video data set.
Yeah,
That really feels like they're trying to push the whole field forward with this.
absolutely. Making it open source lets everyone build on it, test it, apply it to new problems. And that video data set, in particular, is super valuable for training models on that tricky video-text connection.
Okay, let's get into the nuts and bolts then. How do they actually build PE? The paper mentions a two-stage process. What were they trying to achieve, and why split it like that?
So, two main goals. First, make contrastive training more scalable, more data efficient. Second, create one unified model that's good at both images and videos.
Right.
Now, those goals kind of conflict because you have tons of image text data out there, relatively speaking, but high-quality video text data, much harder to come by, much more expensive.
Okay, so the data imbalance forced their hand.
Pretty much. That difference in data availability really led them to this two-stage approach.
Makes sense. Let's break down stage one. Robust image pre-training. What was the focus there, and what tricks did they use to make it robust?
Right. Stage one was all about building a really solid foundation in image understanding. They started with a strong existing model, OpenCLEAP VITL14. That's a vision transformer model. And then they systematically layered on several regularization techniques, things designed to make it perform better, but crucially, make it more robust, better at handling new images, tricky conditions.
And that kind of techniques?
They detail them in Figure 2. Things like progressive resolution, starting training on low-res images, then gradually increasing resolution. ROP, that's rotary positional embeddings, helps it understand spatial layouts better.
Like where things are.
Exactly. Critical for stuff like detection. Then there's attention pooling for summarizing image info smartly, lots of data augmentation, mass regularization to learn more complete representations, and tweaking the batch size.
And Figure 2 actually breaks down how each change affected accuracy on standard ImageNet versus this robustness measure, right? What did they learn from all that tweaking?
Yeah, the figure shows clearly that those refined techniques really boosted robustness, the ability to generalize well beyond the training data. Interestingly, they found ImageNet accuracy seemed to scale more with just adding more data,
Right.
but robustness scaled more with how they trained. These specific methods mattered more for generalization, which kind of tells you just throwing more data isn't always the answer for robustness. You need smarter training.
Okay, Figure 3 and 4 support this too, showing better scaling on tough benchmarks and improvements with longer training using their recipe.
Exactly. It really validates their refined image pre-training approach.
So stage 1, build a super robust image model. Now stage 2, the video data engine and fine-tuning. How do they pivot from the strong image model to handling video?
Okay, so with that strong image model in hand, they built what they call a video data engine. The core idea was to use the image encoder to automatically generate good text descriptions or captions for lots of video clips.
Using the image model to label videos.
Sort of, yeah. It was supported by a new video text dataset they created with human refinement involved. But basically, the process used the image encoder to pull features from video frames, then use those features to generate text describing the video. And then, the final step. They took the robust image encoder from stage 1 and just did a relatively short fine-tuning session on this newly generated video data.
And that short video fine-tuning actually helped both image and video performance.
Significantly. That's the remarkable part. Despite being brief, it boosted performance across the board. It's like teaching the model about static cats first, then using that cat knowledge to help it describe videos of cats playing, and that makes it better at both.
That's a clever feedback loop. Using image skills to create video labels, then using those labels to improve both image and video skills. bootstrapping almost.
Exactly. It let them leverage the image knowledge into the harder video domain without needing mountains of human-labeled video data from scratch.
Let's dig into that video data engine a bit more. 3 phases you mentioned for crafting those captions. Phase 1.
Phase 1 was building a base captioner. They called it the Perception Language Model, or PLM. It used an early PE version for vision and Llama for language. They trained it on a huge mix of images and videos, like 64.7 million of them.
Wow.
Yeah, covering all sorts of stuff. And this base PLM got decent initial scores on standard video captioning benchmarks.
So PLM was the starting point. Phase 2. What happened next?
Phase 2 was about boosting the quality of those automated captions. They mixed in some high-quality video data that already had human-refined captions.
Injecting human expertise.
Right, to make the descriptions more accurate, more detailed, more, human-like than just the raw machine output.
Makes sense. And phase 3 involved LLM summarization using Llama 3.370A.
Yes, the big guns. They used this massive Llama model, gave it a specific prompt, it's in the appendix, and fed it everything. The PLM captions, image-only captions from an earlier Llama, and existing video metadata like titles and descriptions.
Why the metadata?
Because, as they point out in Figure 5, titles and descriptions often have info the captioning models might miss: context, background knowledge. So Llama 3.3 summarized all of that into a final, comprehensive, high-quality caption.
Okay, that's a seriously sophisticated pipeline. Auto-captioning, human refinement, then LLM synthesis. A smart way to build that crucial video data set.
Definitely. And that engine was key to the improvements they saw later.
Let's talk about those improvements, the scaling and performance. Figure 6 shows the impact of using more of this recaptioned video data, right? What did it show?
It clearly showed that adding more of their synthetic video data consistently boosted performance on both image and video benchmarks. You saw steady gains on tough robustness metrics like ObjectNet and ImageNet adversarial, and a big jump in zero-shot retrieval. Finding stuff via text queries got much better. Even standard ImageNet improved, though it eventually leveled off a bit.
So, training with good video text data helps both domains. And they scaled the biggest model, P-Core G, to 2 billion parameters.
Yep, G-scale. Table 4 shows the different sizes they tried: base, B, large L, and giant G. Different parameter counts, different feature dimensions.
And they used distillation to help the smaller B and L models, kind of transferring knowledge from the big G model.
Exactly. They trained the smaller student models to mimic the similarity predictions of the large teacher model. They used KL divergence to measure the difference.
Any tricks to make that work better?
Yeah, they found that making the teacher model more confident in its predictions using a lower softmax temperature actually made the knowledge transfer more effective. A relatively short distillation phase gave the B&L models a nice boost.
So the whole P-Core training recipe, massive image pre-training, then fine-tuning on the recaptioned videos, and finally distillation for the smaller models.
That's the sequence. 5.4 billion image-text pairs for pre-training, 22 million recaptioned videos for fine-tuning, then distillation.
And the results, especially on zero-shot image tasks, they beat some big names, even models trained on Google's huge internal dataset, JFT3B.
Yeah, Table 5 is pretty striking. P-Core beat all the other public contrastive models across the board, including on those tough robustness metrics. And yeah, doing that without JFT is impressive.
And it was top across different categories simultaneously.
Right. State-of-the-art on image-text retrieval, big gains in fine-grained classification. First model to hit the top spot on all those common zero-shot benchmarks at once.
And just training on those 22 million videos gave significant bumps to image understanding.
The numbers are clear. Plus 0.6% average on general image classification, plus 1.2% on the tough benchmarks, plus 1.0% average on fine-grained, and a really nice plus 3.6% average on zero-shot retrieval. It really shows that video data helps learn better general visual features.
What about the video results themselves, Table 6?
Also very strong. P-Core G beat image-only encoders, even beat many dedicated video models on zero-shot video classification. And it nearly matched the state-of-the-art on video retrieval with just a simple frame-level approach.
Without complex temporal modeling.
Right, which again highlights how good that video data engine was. They saw a plus 3.9% average gain in zero-shot video classification and a massive plus 11.1% in retrieval from that video data, using less video data than some others.
They also tested on more diverse benchmarks, didn't they? Table 7, iNaturalist, Dollar Street.
Yep.
Testing long-tail knowledge with iNaturalist, cultural diversity with Dollar Street, OCR with text caps, challenging video retrieval with PVD. P-Core G did well across the board.
And the text caps result was interesting, handling flipped text.
Yeah, even with horizontal flip augmentation during training, which usually messes up OCR, it showed an ability to sort of read backwards. It's just some serious robustness. And it crushed the PVD video retrieval task, too.
Finally, the frozen encoder probing, comparing PeakerG's raw features.
Right, Table 8. Using standard checks like KNN, linear probing on ImageNet, PeakerG came out on top compared to all existing public encoders, even some much larger ones. Just reinforces the quality of the features it learns.
Okay, so Peaker nails classification and retrieval. But the big question, are those features useful for more detailed stuff? Like detection, depth estimation, things that need more spatial smarts.
Exactly. That's the crucial next step covered in Section 3. The common wisdom was often, contrasted for classification, capturing models for language tasks, self-supervised for spatial stuff.
Different tools for different jobs. Right, so they put P-Core's frozen features to the test against models specifically designed for those other areas, AIM-V2 for captioning, Dino-V2 for self-supervised spatial learning. They tested on detection, depth, OCR Q&A, VQA, grounding, tracking, the works.
And Figure 8 summarizes that. How did P-Core do in these more granular areas?
The results were a bit mixed. They called it peaky performance. Like on COSO detection, the best layer in P-Core was competitive with Dino V2, but the very last layer, significantly worse.
So which layer you pull features from really matters.
Critically important, the optimal layer varied a lot depending on the specific downstream task.
Figure 8 also mentions that layer-wise analysis across different task types, classification, language, spatial. What did that show? Where does the information live in the network?
By using different decoders tailored for each task, like a transformer for classification, their PLM setup for language, VTDET or DPT for spatial tasks, they mapped out which layers were strongest for which abilities.
So different skills peak at different depths.
Pretty much. It confirmed that a diverse set of features get learned all through the network layers. It's not all concentrated at the end.
They also looked specifically at how their robust pre-training recipe affected downstream detection performance, right? Figures 9 and 10.
Yeah, they compared the layers from models trained with their improved recipe versus a standard CLIP recipe on COCOSO detection. They found their recipe significantly boosted the performance of the best performing layer.
What parts of the recipe helped most?
Surprisingly, data augmentation and especially that progressive resolution strategy seemed key. They think progressive resolution might encourage more scale invariant features, stopping it from overfitting to the global contrastive task.
But the last layer didn't improve as much.
Right, the last layer's performance kind of stagnated after they introduced progressive resolution, even while the best intermediate layer got much better.
And how did this play out when scaling model size, figure 11?
That showed a really clear difference. With the standard CLIP recipe, the best layer's performance on downstream tasks plateaued pretty quickly as models got bigger. But with their robust recipe, the best layer kept improving all the way up to the G scale.
But the last layer still stagnated.
Yeah, for both recipes, the last layer didn't scale nearly as well for these downstream tasks, which might explain why some previous work concluded contrastive learning doesn't scale well for these tasks. Maybe they were only looking at the last layer.
So the good stuff might be hiding in the middle layers.
Yeah.
Fascinating. Okay, let's switch gears to language alignment. How did they connect P-Core's vision to natural language understanding?
Right, so they needed to adapt P-Core to work with a pre-trained language model, specifically Llama 3. They used a vision projector, basically a small network that translates visual features into the language model's language.
Like a bridge between vision and text spaces.
Exactly. They started with a warm-up phase, just training this projector using image text data, teaching the model to predict the next word and a caption given the image. Then they fine-tuned everything, vision encoder, projector, and the LLM itself on a bigger data set. The resulting vision encoder is called PLang.
And they ran experiments to find the best way to do this alignment. Ablation studies in Table 9.
Yep. They tweaked things like the LLM size, 1B versus 3B params, whether they froze the LLM weights, the projector type, MLP versus simple linear, which P-Core layer to project from, and regularization.
What worked best?
Generally, the bigger 3B Llama model worked better, especially when its weights were allowed to update. A slightly fancier 2-layer MLP projector was better than a linear one. And interestingly, projecting from an intermediate layer of P-Core layer 47 often gave better results than using the very final layer.
Layer 47 again. Seems like the middle layers hold a lot of value. How did PLang compare against other vision encoders used in these big multimodal models? Table 10.
They benchmarked against a bunch of known encoders: Metaclip, Siglip2, Siglip Hype, AIM-V2, Dino V2, Intern VT, different sizes, different training methods. They tried to find the best layer for each encoder for fairness. P-Lang came out looking very strong, showing their alignment method really worked well.
Did it transfer well? Could you plug P-Lang into a different LLM like QuenLM? Table 11 shows that.
Yeah, and the results were really interesting. Even though P-Lang was initially aligned with Llama 3, it performed extremely well with QuenLM 2.5, often beating other encoders, sometimes even InternVT, which was trained with Quen. In some cases, P-Lang actually did better with Quen than with Llama.
Wow, so the visual features it learned were genuinely transferable.
Seems so. Really highlights the generality of the alignment.
And their full system, PLM-8B using P-Lang. How did it stack up against other big open-source multimodal models? Table 12.
It achieved top-tier performance, outperforming well-known models like Elava, Gemma, Quen2VL across a wide range of benchmarks. Really validates P-Lang as a powerful vision backbone for these kinds of systems.
Okay, language alignment seems pretty successful. What about spatial alignment? That sounds trickier.
It is, yeah. As they note in Section 5, there isn't really a standard decoder for all spatial tasks, like there is for language. Their earlier probing already showed P-Core had good spatial features, but the best layer was different for tracking versus detection or depth.
Right, decoders for detection are very different from those for depth or tracking.
Exactly. Different architectures, different input needs, makes a single alignment strategy harder.
And they found something specific about how P-Core handles tracking. Looking at the attention maps in Figure 15.
Yeah, that was cool. Up to about layer 32, the attention seemed pretty local, focusing nearby, but then, boom, around layer 33, these global tokens appear in the background.
Global tokens?
Yeah, tokens that suddenly lots of other parts of the network started paying attention to. It looked like the network shifted gears around layer 33, focusing more on overall semantic understanding than fine-grained spatial detail.
That matters for tracking.
Big time. Tracking needs really precise spatial matching between frames. Those global tokens, losing some fine spatial info, made the later layers less ideal for tracking. Performance peaked around layer 32, just before those global tokens emerged.
Makes sense. So how did they try to spatially align P-Core to get those good earlier spatial features accessible later on?
Their strategy in Figure 16 had a few parts. One was self-alignment, training later layers to match the features of an earlier spatially good layer, like layer 41.
Okay.
Another was aligning to mask predictions from SAM 2.1, the segment anything model, which is great at outlining objects.
Right. Strong spatial signal there.
And the third was combining both self-alignment and SAM alignment. That combination resulted in their P-spatial G model.
How did these different strategies affect performance on spatial tasks? Also Figure 16.
So aligning just to layer 41 was okay for detection, depth, segmentation, but not great for tracking. Aligning just to SAM boosted tracking a lot, but hurt other tasks, probably because mask shapes don't say what the object is.
And the combo. P-spatial.
That seemed to be the sweet spot. Combining self-alignment and SAM alignment lifted good spatial features towards the end of the network and improved performance across most spatial tasks compared to just self-alignment. Tracking dipped slightly compared to pure SAM alignment, but was still way better than baseline, and the other tasks were strong.
And the frozen feature results in Table 13 confirm P-spatial G's strength on tracking, segmentation, depth.
Yes, it performed very well across those dense prediction tasks compared to other general encoders.
And finally, the system-level detection results in Table 15, using P-spatial G with a simple decoder on Cocoa.
That was a big one. It showed P-spatial G with just a simple DETR-style decoder could match the performance of much more complex, specialized detection models. They highlight it as the first general, contrastively pre-trained model to hit that mark on Cocoa.
Very impressive. They also mentioned efficient training techniques and their overall alignment tuning strategies briefly. Sounds like a lot went into making this practical.
Definitely. They talked about large batches, LM optimizer, ROPE, data curation, recaptioning, all for efficient CLIP training. And the alignment tuning, as we covered, was about adapting for language, MLLMs, and boosting spatial skills, using that mix of self-distillation and a spatial teacher like SAM. The goal was always making the core vision encoder as general as possible.
Okay, let's try and wrap this up. What's the absolute key takeaway from this perception encoder deep dive?
I think the main thing is how PE shows that a single, unified, contrastive pre-training approach, when you add smart, targeted alignment for language with P-Lang, for space with P-spatial, can create foundation models that are state-of-the-art across an incredible range of vision tasks for both images and video.
And what was the most surprising thing for you? Or a really cool insight?
For me, it's still that emergence of such diverse skills, reading text, understanding depth from just that global contrastive setup. That and the reading backwards thing on text caps after horizontal flipping, that points to some really interesting flexible representations being learned.
So for you listening, what's the big benefit here? Why care about PE?
Well, PE really points towards potentially simpler yet more powerful AI vision systems.
Mm,
If one core model can be adapted effectively for so many things, it could speed up development and maybe lead to breakthroughs in robotics, content understanding, interaction, lots of areas.
All right, final thought to leave you with. If one AI model can learn to see and grasp the visual world this comprehensively, what does that mean for the future? Do we move away from specialized AIs towards these unified foundation models? And what totally new things become possible when AI vision gets this versatile? Definitely food for thought. And hey, if you want to dig deeper, remember the models, code, and that PE video dataset are out there to explore.